Welcome back, brothers. Today we're diving into a really critical operational explainer. We are looking at Incident 12 from our Crisis Management Manual, the sudden, complete plant blackout. I need you to listen closely to this one, because when the lights go out and the hum of the machinery just stops, panic is absolutely your worst enemy. We're going to slowly and clearly break down exactly what happens to our physiochemical and biological wastewater treatment systems during an unplanned electrical interruption, and exactly how you need to respond to save the plant.
So here's our agenda. We've got 5 sections to cover today: incident definition, severity and system impact, real-time symptoms, root causes, and finally our investigation protocol. Following this structure is key, so let's jump right in.
Section 1, the blackout incident. This is a total electromechanical failure. Imagine the absolute halt of our plant's heartbeat. A sudden blackout means every single critical component just stops dead in its tracks. Your air blowers shut down. Wastewater feed pumps stopped. Both the return-activated sludge and waste-activated sludge pumps lose power instantly. Even your chemical dosing pumps and pneumatic distribution systems go completely offline. In just a matter of seconds, the active mechanical processes keeping our plant alive simply cease to exist.
All right, moving on to section 2, severity and system impact. You've really got to memorize this biological ticking clock, brothers. Without those blowers, your aeration tank loses its dissolved oxygen in just 5 to 15 minutes. By the 30 to 60-minute mark, those aerobic bacteria start suffocating, forcing them into an anaerobic state that leads to rapid decomposition. And on the mechanical side, if water keeps flowing in by gravity without automatic shutoff valves, we're looking at a critical overflow risk in the equalization and aeration tanks within just 1 to 3 hours. Time is absolutely not on our side here.
And to make matters even worse, you're essentially flying blind. When the power drops, the SCADA, PLC, and monitoring screens completely shut down, leaving you with zero data and no alerts. Plus, even if emergency lighting kicks on, these wide plant areas become incredibly dark and hazardous. You've got to really watch your step while trying to manage a rapidly degrading situation. Also, without the RAS pumps running, the sludge in your settling tanks isn't circulating anymore. A thick layer of bottom sludge rapidly builds up, and that can turn anaerobic very quickly. Oh, and there's a secondary danger we have to prep for: inrush current. When the power finally does come back on, simultaneously restarting all those massive motors can either overload the newly restored grid, causing a huge voltage drop, or just trip the breakers, plunging you right back into the dark.
Which brings us to section 3, recognizing the symptoms.
So, how does this actually unfold on the floor? Picture that jarring silence. If you're on shift, the very first symptom is just the sudden, eerie absence of noise. The blowers and pumps go completely quiet, maybe except for the warning beep of a temporary UPS. Within 10 to 20 minutes, that rolling, turbulent agitation on the surface of your aeration tanks, it completely vanishes as the last trapped bubbles pop. The surface just gets unnervingly calm and still. Then, as we hit that 30 to 60-minute mark, the biological breakdown becomes visible and, well, fragrant. You'll start to catch that distinct, foul smell of hydrogen sulfide gas. You'll probably see black or gray foam popping up sporadically across the aeration tank, and the water itself will shift to a dark gray. Over in the settling tanks, carbon dioxide and nitrogen gases from the dying anaerobic sludge will actually cause clumps of it to float right up to the surface. Meanwhile, mechanically speaking, gravity just takes over. Untreated wastewater from the factory might just keep right on flowing into your equalization tank, causing water levels to visibly rise, which is a huge red flag for an impending overflow. At the exact same time, down at the tail end of the plant, the outbound flow to discharge will either slow to a mere trickle or stop entirely, simply because the booster and discharge pumps are dead. But you also have to watch out for the invisible failures happening behind the scenes. Your UV, ozone, or chlorine disinfection systems instantly shut down. After about 15 to 30 minutes, the UPS batteries backing up your sensors and SCADA will start beeping that low battery warning. And, crucially, powered solenoid valves will lose their holding current. They'll revert to their mechanical default positions, meaning they're going to fail closed or fail open, depending entirely on how they were designed. Okay, section 4, identifying possible causes. Think of this matrix as your diagnostic cheat sheet. It crosses the potential cause with the specific symptoms you need to look for. Are we dealing with a high probability event, like a national grid failure? Or maybe a medium probability internal fault, where you might actually smell burning plastic near a control cabinet? Or was it just a sudden overload that tripped a breaker? Let's break these down.
So the highest probability is usually an external grid failure. You can typically spot this right away if the streetlights outside the plant and the whole neighboring block go dark all at once. On the flip side, if the neighbors have power but we don't, we're definitely looking at an internal plant fault. This could be a blown breaker, a short circuit in the motor control center, or some burnt wiring. You'll want to check for smoke or an acrid burning smell right near the main switchboard.
But there are definitely other culprits too. We might have a backup generator that just flat out failed to start because of a weak starter battery, or an automatic transfer switch that didn't flip. Weather is a huge factor too. A severe storm could easily flood a transformer or knock down some lines. And, well, we have to admit there's always that low probability but very real chance of human error, like one of the brothers accidentally tripping the main breaker during routine maintenance, or a contractor cutting a buried cable.
Now, Section 5, the Root Cause Investigation Protocol. All right, let's walk through your immediate actions. Step 1, confirm that external grid status. Look at the surrounding neighborhood or get the power company on the phone. Step 2, head straight to the main switchboard, the MSB. Check if the main breaker's tripped, check those phase lights, and read the internal voltage meters. Step 3, if your plant uses them, you absolutely must inspect the internal transformers. Now keep in mind if the external grid is up but the plant is down, you have to physically inspect those systems. At the MSB, you're looking for tripped switches. At the internal transformers, check those oil levels, look at the temperature gauges, check to see if any fire alarms have triggered, or if any medium voltage fuses have blown. And obviously be extremely cautious and follow every single electrical safety procedure. Okay, what if everything on the main line looks clear but you're still in the dark? Time to shift your attention to the backup power systems. Step 4, verify the diesel generator. Does it actually have fuel? Is the battery charged? Step 5, check the ATS to see if it actually transferred the power load. And Step 6, open up those motor control centers and see exactly which MCC branches might have trips. I really can't emphasize this enough, brothers. These backup systems are notorious points of failure during an emergency. Make sure you check if the generator's control panel is actually set to auto and hasn't been accidentally left in manual mode. Inspect the ATS panel super closely for any red fault lights or mechanical misalignments that might be preventing the switch from closing the circuit. Once the electrical hardware is assessed, we pivot straight to damage control. Step 7, get an estimated time of restoration from the power company. Step 8, calculate exactly how many hours you have until those equalization and aeration tanks spill over based on your current inflow rate. And Step 9, manually verify the positions of all your motorized and solenoid valves. Let me reiterate how absolutely critical it is to know your valves, brothers. If wastewater just keeps flowing into the plant by gravity, but your pumps are completely dead, you are marching straight toward a catastrophic biological spill. You have to manually verify if your critical valves failed open or failed closed. And if necessary, you must manually override and close those inlet valves to isolate the system and buy yourself some much-needed time. We've covered a whole amount of ground today, but it really all boils down to readiness. So I want to leave you with this one actionable question. Do you know the exact location of your plant's manual fail-safe valves? And do you know exactly where the emergency flashlights are kept? Seriously, don't wait to figure this out in the dark. Go back to your plant floors today, physically locate your emergency gear, and make sure you are 100% ready before the lights go out. Stay safe out there, brothers, and I'll catch you in the next explainer.